Hello, my name is Caleb, and this is Lab 1 Constant Velocity. The main purpose of this lab is to compare the observed position of an object over a measured period of time against a predicted computational position of the object over the same time with a constant velocity. The object we used was a roll of tape, the observed position was taken through Tracker, and the predicted position was computed using GlowScript. Newton's second law, also known as the momentum principle, relates the net interaction between a system and its surroundings, or net force, to the observed motion, or change in momentum, of the system. The net force is defined as delta p over delta t, or change in position over change in time, and the velocity update formula, which is derived from the net force formula, is defined as velocity final equals velocity initial plus net force divided by mass times delta t. This means that if there is no net force acting upon the system, then velocity final will equal velocity initial. The procedures we took were recording a video of a roll of tape rolling in a straight line in front of a distance holder, in this case a meter stick, importing the video into Tracker and tracking the ball's position frame by frame, creating a computational model of the ball's position using GlowScript, and comparing the computational model data to the experimental model data. This was the observed position of the ball, or of the roll of tape, taken throughout the video. Each of these dots or red triangles is a different point in the video for the center of mass of the tape, and as you can see in the graph, it appears to have a linear decrease throughout the entire video. The Tracker analysis, we use two different points of time and positions to calculate the average velocity. The average velocity was taken by calculating the change in position over change in time, which yielded us with a negative 0.363 meters per second average velocity in the x direction. The total time of the video was about 1.27 seconds, and the initial position was taken to be 0.425 in the x direction and negative 0.5605 meters in the y direction. This is due to where the graph was placed in the video, which would have changed the initial position. The computational model, as you can see, we used a net force of 0 because there was no net force acting upon the tape for the time that we used. The initial velocity and tape position were both inputted as such. The delta t was set to 0.033 because the video was recorded in 30 FPS, and we used the average velocity to compute the location. This is the observed versus predicted graph. As you can see, the experiment position and the model position are very closely related, though at the end of the graph there is a slight offset from the experiment position from the model position. Some possible errors include rounding errors, which could add deviation to the results, the position tracking, which is different placement for the center of mass during the tracking could cause deviations in the computation, and outside forces, which is things like friction or air resistance that were acting on the system that could have changed the speed or the velocity of the tape. If positive x and negative x were interchanged, this would only affect the slope of the graph, causing it to swap between positive and negative. As you saw before, our graph was in a negative slope. If we were to swap between positive and negative x for where we were tracking, it would cause our graph to be in the positive direction instead of the negative direction. The net force was 0 in the observed case. Even though the plot lines in the graph appeared very similar, the experiment points were facing a slight decline at the end of the graph, showing that there were forces like friction and air resistance acting upon the tape. All the forces acting upon the tape were likely gravity, friction, air resistance and the force from the initial push that would have caused the tape to move.